Okay. Right, I think we've got a long way to drive this morning. So welcome to a day of lectures from me about spectroscopy of Lyman-alpha on this side of redshift 1, very roughly. Today, in this morning's lecture, I'm going to focus on the global properties of galaxies derived by sort of large aperture spectrophotometry that captures all of the Lyman-alpha emission from galaxies. So this is motivated really by making comparisons with high redshift universe and things that Masami talked about in the previous 3 days. So this is really derived from Galax surveys that have captured on the order of 200 local Lyman-alpha emitters. I'll discuss number counts and the evolution of the luminosity function, which boils into the evolution of actually the Lyman-alpha fraction and its escape fraction, and how the universe has changed by a very large factor in the last 7 gigayears. And finally, well, in the second half, I plan to talk about the properties of these galaxies measured by follow-up observations, targeted HST observations, and lots of stuff done from the ground. But if you want a spoiler, we can say from the outset, the Lyman-alpha galaxies, Lyman-alpha emitting galaxies, they're lower mass and they're younger and they're more compact. And they have higher specific star formation rates and they're bluer, less dusty, they're less metallic, something else. They're more strongly ionizing than non-Lyman-alpha emitting galaxies. And for the first time, we also have direct measures of the H1 mass, and we can see that they actually contain less H1 than the non-emitting counterparts. So this again is the sort of picture of Galax surveys, a huge field of view. A huge 1 and a bit degrees field of view. HST, if you zoom in on just one galaxy with a frame here, each HST field corresponds to tiny, tiny, tiny fraction. So actually if you check the area and the delta Z you can do with one shot of a Galax survey, the survey volume is like 5 × 10⁵ cubic megaparsecs, and here it's 5 × 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ observation differ by most precisely a factor of 1,000,000. So in Galax, you're going to get everything in the field of view. It's very much like going to census data for an entire population. Everything that's there you're going to get. HST observations, pre-selected and pointed. It's like going to somebody's Facebook account, hacking it and downloading all of their data. Here's an overview of some of the HST observations that we're doing. I'm putting this in really for lecture notes. I'm not planning really to go through it, but there's, for example, a Lyman-alpha reference sample that we're doing. This is my favorite set of Lyman-alpha observations. We're looking at 55 starbursts with HST, aim to be somewhat comparable to Diamondbreak galaxies. They came kind of continuum magnitudes, stuff found at redshift 3. And there's also a sample of Lyman-Break analogs, designed in the same kind of way, somewhat higher redshift, different criteria on compactness, but also going for the same motivation. There's a little bit of overlap. Similarly, there are green pea samples that we've heard about also already in Masami's talk, and I think at least sort of 10-ish people in the audience work on them or have worked on them, and they also overlap to some extent with Lyman-Break analogs. With our last sample, there was a set of guaranteed time observations performed with the COS that also overlap somewhat. And out down the bottom here, people have been targeting ULERGs. There's some 11-ish ULERGs been observed spectroscopically and another 5 in imaging mode. And also sort of bridging the gap between Galax and HST surveys, there's also group sets of data where we followed up Galax selected Lyman-alpha emitters in high resolution with the Hubble. So this is how the local galaxies really compare with those at high redshift. This is redshift on X here, going between 0 and 4. And you have Lyman-alpha luminosity up the side. So the deepest observations come from very, very, very deep long slit observations up here. They're going down to a little bit more than 10 to the 41 ergs per second. Sort of wide field, shallow IFU observations up here. So 10 to the 43 and a half. And then some deep narrowband observations coming in the middle there, in between. The redshift 1, surveys. Galax is the only machine that could get these galaxies. But at redshift 1, it gets the bright ones, comparable with the most luminous high redshift Lyman-alpha emitters. And in the local universe, you can come down a bit, an order of magnitude in luminosity. These galaxies, on average, they are more comparable with the objects found in the deepest Lyman-alpha surveys at high Z. So sort of bright end of the luminosity function, fainter end of the luminosity function. Green peas, these are the Galax local Lyman-alpha emitters in red. Our HST samples here in a cyan color, one bright one. This is the green peas, roughly the luminosity range there. So you see we're somewhat comparable in luminosities. The bright galaxies, they do exist in the local universe, but you have to survey, you have to go to basically the whole northern sky survey of the Sloan Digital Sky survey in order to find galaxies that are really up there with the most luminous high Z star formers. If you compare them with the dual luminosity function, this is Sebastiano's luminosity function, very deep narrowband observations at redshift 2. We're coming in somewhat sub-L star with Larsen, the Galax Lyman-alpha emitters, green P, somewhat more luminous, getting up there towards the knee of the luminosity function. We want to see the same thing in the continuum. This is the UV continuum luminosity function. L star somewhere around here. It's combining blank field data of Reddy and Steidel with extremely deep lensing observations from Malavian collaborators. The dwarf galaxies we see at low redshift are way down here at the bottom end. Really the faintest galaxies you can ever find at high redshift. Larsen HST surveys coming here somewhat in the middle, and the Galax Lyman-alpha emitters up there almost near the characteristic luminosity. Perhaps talk about this stuff. So how you go about finding galaxies in this slitless data, you have, of course, as I've shown before, you take the image, you put in a disperser, and you disperse everything in the field of view out over the detector, so you get these propeller-like patterns. And you go to non-dispersed data, try and find continuum sources, go very deep, find continuum sources. Look for the in the dispersed light image for where the dispersed continuum of these objects may lie, and you extract them, and you feed them into some line identification tool, and you look for excess of emission lines that look like this. Doesn't show up very well in the light of this room, but there's a strong line there, which is Lyman-alpha. Can't read the axis. But to be very clear about this, what we're not doing quite precisely is Lyman-alpha selection, right? You go into a non-dispersed image, you find an object in the continuum first, and then you go and look for Lyman-alpha emission. So while you see quite often quoted that these surveys are entirely analogous in selection to those at high redshift, the equivalent width cuts are in fact the same, or close to being the same, the selection method is not exactly identical. And it's worth bearing in mind these when you consider the selection function and the evolution of galaxies later. So if you look at what shows up in these surveys, this is the follow-up now from the ground of the sample of redshift 0.3 Lyman-alpha emitters done by Steve Finkelstein, 2009. What you're seeing here is a BPT diagram. On the x-axis is showing you the N2 over H alpha ratio, and on Y here, O3H beta. So this is a way of telling if something is dominated by star formation or dominated by a very, very hard ionizing source like an active galactic nucleus. So here's a sequence of star-forming galaxies out here, ideally. Here you have liners, low ionization nuclear emission line region things. Cepheid galaxies fall up here, and this emission line ratio diagram. And then also, since many of these Galax survey fields were looking in areas where there were deep HST observations, deep Chandra and deep Spitzer, they could also go and look for mid-infrared emission that could be characteristic of AGN at 24 micron, X-ray emission for sure. We have BTT diagram diagnostic here. And go and look for high ionization lines, neon 5, helium 2, and also the presence of broad lines. And if you add up things that could be classified as AGN by any individual, any of these single classification schemes for AGN, you arrive actually at a surprisingly high number of about 40%. Now you can argue, of course, that some of these high ionization lines, they could be made by very hot stellar populations. We could bring this number down somewhat, but the bottom line here is going to be that you're not going to bring this number of 40% down anywhere near the 5% that you see in narrowband selected Lyman-alpha surveys at redshift 2, and maybe even, well, almost certainly even lower at higher redshift. So there are more AGN in a pure locally selected Lyman-alpha sample. Perhaps that's not entirely unexpected. These are the number counts, so how many of the local emitters, I mean here on the x-axis you have near UV magnitude, on the y you have the number per square degree per magnitude. So it's not quite a luminosity function, just telling you how many sources of a given magnitude there are on the sky. The important lines to look at here is this sort of continuum UV number counts derived by Stefan Arnault. These are selected also from Galax continuum surveys, but in the redshift range 0.2 to 0.4. And of course, as usual, there's not very many bright sources and many faint ones. There's a fit to the data there. If you look at the blue points, this is the number counts for Lyman-alpha selected galaxies with equivalent widths. No, galaxies with Lyman-alpha emission lines of equivalent width greater than 20 angstroms, and in red, greater than 45 angstroms. And these dashed and dotted lines, here is simply this curve for the whole number counts multiplied by 0.05, 0.01. And you can see that Lyman-alpha emitting galaxies, strong Lyman-alpha emitters, are representing about 5% of the local near UV number counts. So they're rare, right? We're seeing a few percent UV selected galaxies emitting strong Lyman-alpha. You compare this to redshift 2 and 3. Here we're seeing 10, 25% in Alice Shapley's compilation from 2003. Numbers that go up to 50% by redshift 5 from Dan Stark's papers and others. And so here we're seeing really a strong evolution in the number of UV selected galaxies that emit their Lyman-alpha. It's in decline by a factor of 5 since redshift 2. The same thing really cast in luminosity function. So we have Lyman-alpha luminosity here now on X increasing, faint to bright. We have the number of galaxies per cosmic volume per luminosity. The blue line that we're seeing, no it's not. Yeah, it is. The black points that we're seeing here are derived from the Galax data. So this is very few, very bright galaxies. This is probably also where the majority of the AGN are sitting at the bright end of the luminosity function. And then what you're seeing in red is the local H-alpha luminosity function derived at the same redshift. It's Tress and Maddox, I think. And you see that the H-alpha luminosity function actually sits above the Lyman-alpha luminosity function. And if you look down the blue points here, these are actually the same LF at the same redshift derived from H-beta. And that blue points there actually look like a decent continuation of the black points. It seems if you were to extrapolate this luminosity function from Lyman-alpha, you get back the H-beta luminosity function at low redshift, which is quite surprising given that, as we know, as we've seen before, Lyman-alpha is intrinsically 30 times brighter than H-beta is. So there is, the universe, it's another way of writing that the universe is significantly underluminous in Lyman-alpha compared to how much it's really producing. You can write down, you have enough data points here to do a fit through the luminosity function data points. You can derive Schechter parameters. Here we're talking of a characteristic luminosity L star of 10 to the 41.6 compared to 10 times brighter than that. Redshift 3, that's shown up here, this red luminosity function from Carol Gronval. 5 stars also differing by a large factor. You take the product of these two numbers. You see that the Lyman-alpha luminosity density of the universe has decreased by about 40 times over the last 8 giga-years between redshift 3 and 0.3. Everybody paying attention? All good on the local Lyman-alpha luminosity function? And the pot is just to make sure you're paying attention. Okay, so Galax had a near UV channel too. This is from the same set of papers by Len Cowie, looking in the near UV dispersed images to look for Lyman-alpha emitters. The luminosity function there at the bright end, you see some galaxies there. It's kind of a bit messy. It's not encouraging for deriving Schechter parameters at redshift 1. This is going back to largely to selection. I don't want to talk too much about this because it's quite complicated. If you rely on the pipeline data and go, as I said, through the non-dispersed images, look for continuum sources, and then go and look for Lyman-alpha emitters, you find one sample of galaxies. This is quite an interesting way of processing the data derived in a paper by Amy Barger in 2012. You see that the data have been obtained on very many position angles, and I don't want to dwell too much on this slide because it's methodological, it's complicated, and it's described in great detail in the paper. But the bottom line is that, any point on an image, you look at a pixel on a dispersed image, you see here, and you know the angle of the dispersion. So light falling on any given pixel can come from a galaxy at any position along the dispersion axis, just from a different wavelength. And if you have if you have observations obtained on very many different position angles, you put your galaxy in the center, and this circular line drawn around here corresponds to a constant wavelength. And if you're clever and you build up a big matrix of x pixels by y pixels by the number of wavelength elements, by the number of images, you can play some clever game, and probably involving a matrix inversion. I'm not really sure. The methods derive yourself a data cube. Data cube is simply a matrix of x by y by lambda. And that's very nice if you're looking for galaxies, because if you have a data cube, then you can go and do like pseudo narrowband images and look for excess sources. Here's just an example of some of these frames. Here you see a pseudo narrowband image derived from the data cube, little spot there, and near you image with loads of stuff in it. Here you see one narrowband, nothing there. The next one in wavelength, oh, there's a galaxy in there. Next one in wavelength, a galaxy has gone away. It's because, of course, there was a bright Lyman-alpha emission line in one of those narrowbands, and the other one was just sampling this very faint continuum. This is nice because it enables you to actually go and do proper emission line selection. And emission line selection is what they were doing at high redshift. This is kind of perhaps a difficult plot to read, but it's also quite illustrative when we get to the bottom of it. On X, you have the near UV magnitude of the samples recovered by various methods, and on Y, you have redshift. So the black point are the points found by the standard pipeline methods, and looking for continuum sources first. And the blue points are the points identified by going to look in the data cube. The black points, anything with the red around it, is an AGN. So you see that the new objects recovered from the data cube, they're out here, 24th, 23rd magnitude, much fainter than the majority of the black points. And this is the same thing cast by Lyman-alpha luminosity down there. You have the sort of pipeline data and the new data cube data in blue. When you take the AGN off these figures, it's really, really revealing. What you're seeing down here is new blue galaxies, much fainter than before, identified. Probably they're the star-forming ones. If you look at the AGN fraction as a function of luminosity in these samples, it's really quite significant here at the very bright end at 10 to the 43 ergs per second. The AGN fraction is 0.7, so 70% of the things in the survey are AGN. Down here, an order of magnitude fainter, we're in the, well, big difference here, 10, 20, 30% regime. If you look at the images of these AGN, you see, of course, they're bright. They have bright point-like nuclei. These are ground-based data, but they're all point-like, bright. In the same data, star-forming galaxies at redshift 1 appear much less bright and much feebler. They actually, in this light, some of them aren't even really showing up at all. Now also with narrowband selection or narrowband-like selection, you can go and do the first real surveys for extended Lyman-alpha emission at redshift, well, anywhere below redshift 2. This is the only known sort of extended Lyman-alpha fuzz blob at redshift 1. This is extended over I think 80 kiloparsecs, so it's comparable in size to the high redshift sources. It's actually not particularly bright. It's 10 to the 43-ish ergs per second, so it's not Sebastiano type slug objects by any means, but in the whole Galax, in all of the Galax surveys done at redshift 1, this was the only such object that showed up. It's a volume similar to that surveyed at redshift 3 by Matsuda and collaborators. This is showing us that these things probably are not particularly common this side of redshift 2. So let's have a look at the evolution in a bit more detail. Here we have now, we can really fit Schechter parameters to the redshift 1 luminosity function. So here we have our redshift 0.3 from Galax, redshift 1 from Galax, and the ground-based narrowband surveys coming up here. You see that the luminosity function has evolved significantly. As I said, in the integral, a factor of 40 between here and here. It's the luminosity density of the universe in Lyman-alpha. Looking at the Schechter parameters here in the local universe, again, L star 41.6. By the time we get to 1, it's gone up by an order of magnitude, roughly, and this is that fact comparable with those measured at redshift 3. So this is telling us that between here and here, redshift 3 and 1, the characteristic luminosity of Lyman-alpha galaxies hasn't really changed at all. All the evolution seems to be happening in the density of galaxies. I mean, here you have 10 to the 1 galaxy per cubic megaparsec roughly. Here we're looking at 1 per roughly 30 cubic megaparsecs, which is quite significant evolution. I'm not sure this is fully understood, that going from the peak of cosmic star formation rate density at redshift 2 and 3, first of all the evolution seems to happen in number density. For some reason Lyman-alpha galaxies are turning off, and then when you go from redshift 1 to redshift 0.3, the same population seems to be getting fainter. I'm not sure this is understood, but it's true. It's certainly quite intriguing. This is the evolution of the Lyman-alpha escape fraction. Again, Masami showed us this a couple of times in the last few days. These are the same thing, the same data roughly from Isaac Wald's paper, and the redshift 1 escape fraction sits nicely there on the plot that wasn't there. These data weren't in existence when we first derived this. So that's what I wanted to say about the evolution of the Lyman-alpha galaxies themselves, just based upon Lyman-alpha and the near UV data. The nice thing about having these large samples of galaxies at redshift 0.3 is that, of course, it's obvious, we can then go and follow them up with anything that we want to. They're near enough to see with even moderate telescopes on the ground, and they're near enough to see with lots of things. So there have been, the first paper on these data came out in 2008 by Jean-Michel de Harving. Notice that in 2009 there were 1, 2, 3, 4 follow-up papers done, and people were quite enthusiastic to jump on these samples in the beginning. In fact, Len Cowie's reanalysis of the data came a year after that, 2010 and 2011. People have been studying dust and metallicity in particular. These are pretty easy. You do them with optical emission lines. Dust, AGN, stellar populations, SED fitting, all the stuff you do at high redshift, except you do it with loads more data points, and you do it with loads higher signal to noise. And you can go and find things like weak emission lines, metallicity diagnostics, etc. We start with some of the morphologies done by Len Cowie. Not sure this is a statistically robust result, but it's kind of interesting to note that if you look at the Lyman-alpha emitting samples and the non-emitting samples at the same redshift, the same continuum luminosities, you see that there is, first of all, tentative evidence that Lyman-alpha emitters are more compact than the non-emitting counterparts of the given luminosity. This is, to me, a particularly interesting result because it's the compact star-forming galaxies that we think are going to be the most efficient at driving very strong winds. Later we're going to see, and probably already everybody knows, that a lot of people think winds are very, very important for the emission Lyman-alpha radiation, and we'll talk about that this afternoon. Also, if you look at the spiral galaxies in the same samples, Lyman-alpha emitters, there seems to be a surprisingly large fraction of spiral galaxies that are face-on compared to edge-on. This is a simulation, a load of radiation transfer simulations done by UN. Here you show the inclination of a galaxy. Here we show the equivalent width you observe in Lyman-alpha. Going from edge-on, equivalent widths low, not really seen as a Lyman-alpha emitter. Face-on galaxies, equivalent widths high. We could be seeing, possibly, that Lyman-alpha likes to escape away from disks more than it likes to escape through disks, which is intuitive, at least. So we would also like to talk about, of course, the dust attenuation in these galaxies. Lyman-alpha, being in the far ultraviolet, probably doesn't like dust very much. It's where the dust attenuation peaks. Masami also showed this diagram by Hakim Matek from 2014. We're seeing here escape fraction in log against nebular dust attenuation written up as EB minus V. 0 is here. These galaxies are actually negatively attenuated, maybe not within the error bars, but over a couple of orders of magnitude and a couple of half a magnitude in EB minus V, there is a strong anti-correlation between the escape fraction and the dust attenuation, as you would very much expect. Did the same thing years earlier as well. This is a compilation. Hold on. The data, same samples, different telescopes, different observations, different fields by Claudio Scalata. Same kind of thing, Lyman-alpha over H-alpha, H-alpha over H-beta. Not exactly the same numbers, but the same stuff. Bright, strong Lyman-alpha emission, low dust content, but also you're seeing a large number of galaxies with significant Lyman-alpha emission, but also quite reddened. If you look at the dotted line on this diagram, I think that's the Cardelli extinction law. Most of the galaxies lie beneath what you would expect here. That's the effects of multiple scatterings, increasing the likelihood that Lyman-alpha will be absorbed by dust. But at the same time, we see a number of galaxies up here that seem to emit too much Lyman-alpha for the amount of dust that they have. Masami also mentioned this in other surveys seen at High Z, HEDDEX pilot survey in particular. So it doesn't look like any extinction or attenuation law that we know. It seems, in fact, to be stuff that was already seen in 1980 in the IUE samples, that sometimes galaxies emit surprisingly much Lyman-alpha, given the fact that they have a lot of dust in them. So I want to say, I can put a bracket into this lecture and talk about dust geometries, because it's going to be really important, right? Dust attenuation laws, dust extinction laws, extinction laws are derived, they're derived from stars, right? The extinction law. You look in the galaxy somewhere in the LMC and the SMC, you look at a star, and you know when you look at a star that all the dust is on this side of the star. It's behaving like a screen, it's a point source with one sight line. You can scatter dust out of the line of sight, but you can't scatter dust into the line of sight. And it's the same with quasars, basically. And dust can exist in many geometries. It's the screen, the way that almost everything is derived and implemented. But this screen doesn't have to, of course, be one solid slab. It's likely to be clumpy, and it's going to affect the shape of the extinction law, right? This is going to make stuff redder if it's a reddening law. If you make this distribution clumpy and you make all the clumps optically thick, then you're just going to make everything fainter without changing the color. And if you put the screen nearer to the stars, then you can also have, here you're going to have extinction, and scattering out of the line of sight. You put the absorbing material close to the stars, you can have scattering back into the line of sight. It very much complicates the attenuation. Or you can go and mix the stars and the dust completely homogeneously, and attenuation behaves very differently in all of these limits. And these are complicated because they involve scattering into the line of sight. These are okay, easily parameterized mathematically. And we explored a few of these in 2009, Claudia did. We explored the single, uniform dust screen. This is where the throughput light at log I over I naught is going as simply minus tau. It's e to the minus tau. That's simple. That's the way all absorption is usually written up. And if you mix perfectly the stars and the stars, this should be nebulae, right? It's Lyman-alpha, but the emitting regions and the dust, you mix everything together perfectly. It's also very simple to solve. You end up with log over I naught is going as, it's 1 minus e to the tau, all divided by tau, so in the high optical depth limit, this is just going as 1 over the optical depth. And then you have a more complicated situation where we write up, if you assume all the dust is located in clumps, all of a given optical depth tau, with a number distribution in the line of sight derived, characterized by a Poisson distribution. You can write down this formula here. It was done in the mid-80s by Nathan Panagia, Kaplan de Haveng. It's not anything new, but it's really very much changes the way light gets through dust as a function of geometry. And this is the result of that study. So again, we have Lyman-alpha H beta fluxes on Y and H alpha H beta, the normal measure of dust reddening on X. And we have points all over the plot. This thick black line is the Milky Way extinction law. Well, doesn't describe very much of the data. Here you have the points below. They're not really a problem because you can do that with resonance scattering. Just make the path of Lyman-alpha longer. But these points up here are very much harder to explain in this way. This is then, so here in this expression for the clumpy dust screen, we have a number of clumps along the line of sight and the optical depth of each clump. And that allows us to draw lines all over this diagram, right? So as you increase the optical depth of the clumps, you do start to redden. You have a load of clumps in the line of sight, you increase the optical depth of each one, you start to make the light that passes through them redder, up until a certain point, right? When they all start to become optically thick, when all the clumps are optically thick, they don't redden anymore, they just suppress the light. And the whole light that gets through is then going to be just dependent upon the number of clumps along the line of sight. So these curves come down and then they start to go back up again. So when they're all completely optically thick, it's like if you put filters in front of the projector, the board there, you change the color. If you put bricks in front of the board, you don't change the color, you just dim the light that comes from it. And that's the high optical depth limit. And here you can you can draw points through all of these points we couldn't explain before. We don't need to invoke anything like this Neufeld-like scattering, Lyman-alpha equivalent width enhancement. We don't believe that to be necessary. The analogy we have to think of, it's just like U-lurgs, right? U-lurgs, if you add up all the reddening and the dust in a U-lurg and convert that to a EB minus V and extrapolate it into the far UV and compute how much UV radiation gets out, you're going to come up with a tiny, tiny number. But it's just light produced at different optical depths and the dust is clumpy. Dust is not distributed as screens in front of galaxies. And whenever you apply an extinction law, you're basically assuming that it is. These were data from, these are all Lyman-alpha selected galaxies from the Galax surveys, to point out that when we do the same thing with HST surveys, UV continuum selected, we find effectively the same result. So Cardelli extinction law down there, we see again points sitting way up, too much Lyman-alpha in principle for EB minus V, assuming the dust is distributed as a screen. Take this Poissonian distribution of clumps and you can draw lines up there. It's all good. So this is data from the last sample now. I'm going to go through many different points in one go. Here we have always escape fraction on the y-axis, right? The And the amount of Lyman-alpha that gets out, measured in large apertures and Lyman-alpha images against here stellar mass divided by SED fitting, the age of the starburst episode derived by SED fitting, the size of a galaxy, the UV radius, I think this is Petrosian radii in kiloparsec. And we have the H-alpha equivalent width, which is casting really the specific star formation rate, the star formation rate divided by the R-band magnitude, roughly tracing out the stellar mass. UV slope beta, so you can say that's dust attenuation if you like. Also it's encoding the age a bit. EB minus V gas, that's H-alpha H beta, we were discussing for the last 5 minutes. N2 index is tracing metallicity, O3, O2 ratio, it's tracing how much, size of the O3 zones compared to the O2 zones, or the hardness, the ionization parameter, if you want to see if the whole ISM is very, very highly ionized, possibly in fact ionized to the end of all the matter. And you see from these plots here that we don't have a very, very large sample, but we have pretty good data, is that in each one of these plots there's peak where all the Lyman-alpha galaxies are sticking up. And that is actually occurring here, where the stellar mass is low, where the galaxies are young, where the galaxies are compact, where the galaxies have a high specific star formation rate. Where they're blue, which could mean they don't have very much dust, and indeed, when you measure how much dust they have, that's kind of consistent. For them to be the less metallic ones, they seem to be the most strongly ionizing ones. Of course, all of these quantities are correlated in galaxies. I'll be done. This is, of course, not independent quantities. This is UV selected galaxies observed with HST. Go back to the Galax sample, then Cowie's study from 2010 and 2011. Seeing here is the histogram of this is the N2 index, so we have low metallicity galaxies down here and high metallicity galaxies up here. The blue things up here are near UV selected galaxies of the same luminosity. The red things are the Lyman-alpha emitters. Clearly the distribution is very, very different, with the Lyman-alpha emitters skewed towards low metallicity. If you look at the H-alpha equivalent width of the non-emitters in blue against the emitters in red, you're looking up here at H-alpha equivalent widths above 100 angstroms. The vast majority of the galaxies are indeed Lyman-alpha emitters. It's a log histogram. You look down here at low specific star formation rates. They're not representing the bulk of the galaxy population. Here, the Lyman-alpha emitters that we see, this 1 out of 20 that we see, we saw before from the Galax sample, those are the ones, the tail, the high specific star formation rate tail. Star formation rate seems broadly consistent between the emitters and the non-emitters, but if you look into the masses, the histogram of emitting galaxies is more extended to the low mass end. And here we're seeing the age derived by SED fitting, just like we did, against the equivalent width in H-alpha. Of course, youngest galaxies produce the most ionizing photons, so the emission line should be strongest. But the red galaxies are the Lyman-alpha emitting ones. Everything up here is Lyman-alpha emitting. The blue ones are the continuum selected galaxies. You see again, the result with Lyman-alpha selected galaxies is the same with the UV continuum. They're low metallicity, they have high specific star formation rates, they're younger, and they're less massive. And again, all of these quantities are not independent quantities. So when we selected galaxies for the LAR study, we picked them out to be at redshift between 0.3 and 0.2. And of course that was so we can study them with HST, they're local enough to go and get all this good data. So Lyman-alpha, of course, is a radiation transfer problem, and that's really depends on where the H1 is. We care about where the H1 is and how much it's moving. That's what's really going to govern if Lyman-alpha is going to meet some dust or not, if a galaxy is going to be Lyman-alpha bright. These observations require that you look for galaxies to be at redshift beyond 0.01 I said this the other day, this is to shift Lyman-alpha out of the Milky Way H1 absorption so it gets through our galaxy and into our telescopes. This puts a lower limit on the distance of about 40 megaparsecs. And to do things efficiently with the HST, this 0.01 has to go to almost 0.03, which is 120 megaparsecs. And that's it's nice for HST, nice for getting UV observations. It's terrible for getting radio observations. It's particularly at 21 centimeter. So we, of course, want to go and probe the atomic gas directly. 21 centimeter, we do this. This is a nice image from the Thing sample from Fabian Walters. Beautiful study of local galaxies in H1. When we're looking out here at 120 megaparsecs, we're not going to get these data. They're not going to be as good as this. Beams are large. But we did do one galaxy at 0.01 before. This is ESO 338 IGO4. It's a great Lyman-Break analog. It's probably I would call it the most local Lyman-Break analog galaxy. There it is in all its glory with HST. There it is scaled onto the size of the VLA observations. There is the galaxy up there. You're seeing that there's a companion over there. There is tidal debris connecting the two. Here with H1 observations like this, we're really probing environment. It seems that this interaction some 100 mega years ago could have stripped all the gas out of it, well, stripped some of the gas out of this galaxy. We can measure column densities. The central column density here in this galaxy peaks at above 10 to the 21 per centimeter square. Now that's sufficiently bright to damp out all of the Lyman-alpha emission, yet we still see bright Lyman-alpha emission. This ISM is not going to be completely homogeneous, if only we could get down to the scales to see it. So these are the tools that we use, the Green Bank telescope, 100 meter radio telescope here, the VLA, just to compare the resolutions of these things a bit. HST, exquisite spatial resolution, 0.05 arc seconds. Green Bank telescope, 9 arc minute beam. VLA config D, 40 arc seconds, only a tiny bit bigger than the HST field of view. Config C, going down here, config A, you can get up the largest. You pull all these dishes as far away as you can take them. You get down to 2 arc seconds, about the size of the HST apertures. So given that the Green Bank telescope has a 9 arc minute beam, a terrible comparison to make with 0.05 arc second resolution of HST, we decided to go and observe all the last galaxies with the Green Bank telescope. Here are some of the data. We were all detected in 21 centimeter, 11 of 14 we got. They have, this is velocity, they have profiles that look like this, double horn, they're rotators. They don't look like that in the images, but there's gas in all these galaxies. 9 arc second beams like this, there could be anything in the beam. You're really probing environment when we look at them. However, we see, I clipped off the bottom of the axis. You can't see the scale. I apologize. But it's mass, increasing H1 mass and increasing H1, it's up the top. Line width in kilometers per second, mass in solar masses in H1, right? Stop laughing. And again, we're seeing the same thing, right? That the strong Lyman-alpha emitting galaxies, escape fraction on Y, is that, and line widths here. Again, the Lyman-alpha emitters in our sample, they have low H1 masses. Just like to point that out, they have low H1 masses, there is less H1 in these galaxies. That doesn't mean that the column density is lower. Doesn't mean the optical depth through H1 is low. And we're going to come back to that this afternoon. Briefly, very briefly I suppose, some observations that we have got some, these are in this paper by Stephen Pardee. We published the GBT data, the masses, and we also had VLA lowest resolution configuration D for 5 galaxies. You're starting to see even the worst, the coarsest spatial resolution, signs of rotation. Of course, there's the HST image. The little tiny red box in there is the size of the HST field. Here is the intensity contours where we see H1. It's resolved, it's rotating, it's coming, receding there, oncoming here. This is a fantastic system, the HST image there. This is a merging pair of Eulergs. There's this huge pile of 10 to the 9 solar masses of H1 just ejected by the merger of these two galaxies. They're nice data. They're 40 arc seconds. The resolution is the same size as the HST field of view. But this is the way you get H1 data. We have the same configuration data coming for the entire, not the entire, for 3/4 of the Lars and extended Lars samples, so 35, I think, galaxies. Data are there now. We've got higher resolution data for a couple, configs B and C. I might present those tomorrow. This is a work in progress. It's first time we've tried to do this. It takes a very, very long time to go to high resolutions in H1, but we're making progress. Everybody paying attention? Good. So there's the summary of the lecture. We've been discussing how to find galaxies at low redshift with Lyman-alpha, surveys with Galax and pointed observations with HST. We know that there are many fewer Lyman-alpha emitters at low Z than there are at high, sort of 5% instead of 25%. And we know that the Lyman-alpha luminosity density of the universe is really crashing between redshift 2 and 3 now. There's one Lyman-alpha blob in all that space. Escape fraction is generally low, but often higher than dust would allow you to estimate. Probably this is because the dust is not homogeneously distributed, and when you compute an EB minus V for a large surface of emission, you have to be cognizant of the fact that you're boiling everything down to one number that may not be representative of the total amount of light that gets out. Lyman-alpha emitters are lower mass and they're younger and more compact, more strongly ionizing. They have less H1 mass, but again, all of these are not independent quantities. They're all related with each other. Pulling out which ones of these are the most important for Lyman-alpha emission is not a straightforward task. It's going to need still really large samples of galaxies. It's the end of part 3. Any questions? Any questions? Oh yeah, sorry, there. Yes?
So I have a question about the dust and how they tend to change depending on the different distributions.
Yep.
So when observers with dust collections, do they have a superposition of the different models, or how do they pick what model they are from, or how is it?
When observers do this,
Yeah.
in like SED fitting, for example,
Yeah.
I mean, so what they usually do is use, most frequently, people working at high redshift apply the Calvetti 1994 2000 attenuation curve to their data. This was derived in a sample of 40 star-forming galaxies in the 1990s. Those IUE spectra I showed the other day were how these data were compiled. They took large aperture continuum observations and the UV spectra, and as a function of, I can't remember how she normalized it, but the bottom line is that unlike the attenuation laws from like the galaxy where you know the dust is in front of you, you are measuring a mixture, an implicit mixture of stars and gas. So this geometry is somehow encoded in the Calvetti law, and these geometries are going to be changing as a function of the total amount of dust in the galaxies and probably the dust distribution. So all these are somehow, in there you're going to have scattering out of the line of sight, scattering into the line of sight. It's all dependent on the, what do you call it? You call the likelihood of being scattered versus? Albedo, thank you. Dependent on that, how that changes with wavelength. So all of this is probably, it's wrapped up in the Calvetti law somehow in a way we don't really understand. What we normally do is apply extinction laws out of the box. And, if you're applying extinction laws derived from starburst galaxies to massive galaxies in the high redshift universe, then, you're not actually using the laws correctly. But, yeah, it's measuring dust attenuation through SEDs is, it's very, very easy to do, and it's not necessarily clear how to interpret the answer. Michael, you also had a question.
Yeah, in the middle of the radio on the last slide, it looked like the H1 was oriented perpendicular to the main axis of the optical, if you can call it. Is that the whole, I mean, the GBT field of view is much larger. Is that a...
These are VLA, do you mean this?
Yeah, no.
These are VLA data,
Okay.
but say, what was it again?
Is it true that the orientation, it looks like in the optical image of Lyman-alpha image, it looks like it's oriented...
Which one?
north,
1, 2, 3.
The middle. Column. But the H1 rotates perpendicular, roughly.
Yeah.
It's oriented towards the northwest and...
It is, and it's rotating. I mean, the thing is rotating like this. Like this, right?
Yeah.
And you think it should be rotating like this from the...
Is it meaningful, the orientation of the H1 versus the optical?
I don't think it's unmeaningful, given that these are the data.
Well, what is the larger field of view like?
The one beam is the size of the blue ellipse up there. I don't know, what was the question again? Is it meaningful? Yes, but what was it? Tell me again.
Well, is it a sign of something else going on
Oh,
the
probably.
larger scale?
Well, I don't know. Probably. I mean, chances are this is a merger, so the H1 reacts early and in complicated ways to the merging of galaxies. Most of the galaxies in this sample are mergers. There's no, if you look in the deep optical images of this galaxy, it's not like a regular disk or anything. Well, not to the surface brightnesses we can see anyway. I think probably this is affected by there having been a merger in the recent past, so this H1 velocity field is rather difficult to interpret. Anybody else? Coffee time? People seem positive about coffee.